We have explained the resumption and treatment of radioactive accumulated water of Fukushima Daiichi nuclear power station several times. This is the last explanation, and we would like to talk about the water amount at each tank and our plans to manage the storage of water and improve the reliability of the water treatment facility. The first page shows the composition of the whole system. There are 4 types of tanks in the south side of units 1 to 4. I will explain the 3 types of tanks. Tanks for fresh water, shown in light blue, reuse water through water desalination. Tanks for concentrated seawater store concentrated brine through the RO membrane, shown in green. Tanks for concentrated wastewater are used for concentrated brine through evaporative concentration type water desalination. Moreover, accumulated water in the turbine buildings is being currently transferred to the process main building and the high temperature incinerator building and then treated. We also prepared tanks for highly concentrated accumulated water as a spare system in case the amount of accumulated water significantly increases or the water treatment facility ceases to operate normally. Regarding accumulated water in the Unit 5 and 6 turbine buildings on the north side, there is leakage of underground water, etc. Therefore, tanks for the lowly concentrated accumulated water and megafloat on the sea surface have been installed. The amount of water in Units 1 to 4 in the south area is 90,000 cubic meters, and the accumulated water in the north area is stored in the megafloat, and so on. As explained before, we prepare tanks for highly concentrated accumulated water, tanks for freshwater, and concentrated seawater. Tanks for highly concentrated accumulated water, shown in the left side, stores concentrated waste with 10 to the 6th power becquerel per cubic centimeters. This tank is placed underground after the inside of the tank is treated. The capacity is 100 cubic meters per tank. Regarding tanks for freshwater and concentrated seawater, the capacity of the round-shaped tanks in the picture is 1,000 cubic meters. On the other hand, the rectangular-shaped tank has an approximate 450 cubic meter capacity. These kinds of tanks are currently installed in the power station. Tanks for lowly accumulated water are installed in the north of Units 5 and 6. The megafloat shown in the right side picture is also for lowly accumulated water. The megafloat has a total capacity of 10,000 cubic meters, and 8,000 cubic meters is set as the operational level. I will explain the current layout of the tanks and the storage capacity. Regarding treatment facilities for low radioactive accumulated water in the north area, the megafloat stores 7,939 cubic meters that accounts for 99% of its 8,000 cubic meter capacity. The accumulated water of the Unit 5 and 6 turbine buildings shown on the right side is stored in the tanks for low radioactive accumulated water. The tank stores 8,048 cubic meters out of its 10,800 cubic meter capacity. Tanks for concentrated wastewater store 3,534 cubic meters out of its capacity of 9,500 cubic meters. Tanks for freshwater store 7,132 cubic meters out of 85,600 cubic meters. Moreover, tanks for concentrated seawater use 78,316 cubic meters out of 85,600 cubic meters. Tanks for highly concentrated accumulated water have a capacity of 2,800 cubic meters. However, these tanks store no water because water treatment is done in order. The next slide shows the installation timeline. The green and orange color lines describe the tank capacity and the storage amount, respectively. For the present, the tank capacity is assumed to be sufficient enough to deal with the accumulated water. The tank capacity for concentrated seawater, shown by the green line, decreases temporarily. This is because the tanks for concentrated seawater were partially used as tanks for concentrated wastewater. That is the reason for the decrease of the tank capacity. For freshwater reuse, the low-level contaminated accumulated water has been sprayed within the site. The radioactive density of the water sprinkled is shown on the table. These results meet WHO standards. Especially the iodine and cesium levels are below the detected limits. Also, all alpha nuclides, all beta nuclides, strontium 89 and 90 levels are below the detected limits. However, the tritium level is 2.6 times 10 to the 0 power per cubic centimeter. Regarding the situation of the water sprinkling, please read the 7th page. There are plans to sprinkle water over the wood, cut down tree yards, and the road within the site, which are approximately 1.2 million square meters. Approximately 1,800 cubic meters of water was sprayed by November 8th. On the 8th page, we would like to introduce the radioactive density of contained water in the north and south tanks. The cesium level of the low-level accumulated water tank, the finished water treatment, dropped to the level of 10 to the minus second, and the level of the fresh water tank is not detectable. On the other hand, the cesium level of the concentrated waste liquid tank has increased greatly and is reaching the level of 10 to the 1. However, all of the beta nuclides are lingering in the tank. The level of the low-level accumulated water tank is 1 times 10 to the second power becquerel per cubic centimeter. The level of the contaminated waste liquid tank is approximately 10 to the 5th power becquerel per cubic centimeter. The reason is that the cesium absorption apparatus is incapable of cleaning out all of the beta nuclides. This is the water amount at the tank and an analysis of the contained water. In addition, there is one other theme that we would like to touch on, the reliability enhancement of the water treatment facilities. We did a test drive of the water treatment facilities late this June, and these facilities have been operated. Its low operating rate continued for some time, but it is now operating stably. The reason we achieved this status is that we received counseling from the Nuclear and Industrial Safety Agency and developed preventive measures for these accidents. We are continuously considering various improvements for operations and planning to analyze failure cases and measures to improve the reliability of the water treatment facilities. These measures will focus on the following 3 points. First, avoid shutdowns of the water treatment facility due to equipment failure. Second, avoid long shutdowns due to failures by securing spares for those components with high failure frequency and that take a long time to obtain. Third, reduce the risk of leakage. A sample case of our considerations is shown on the final page. All of the pumps installed in the skids of the cesium absorption apparatus, Curion, have broken down. Then the water is transferred via the water treatment transferring pumps of the oil separators. See the figure. Its maintenance is difficult due to high radiation in the case of equipment failure because these pumps are in the skid. Therefore, we are planning to install additional pumps at the outside of the skids for maintenance. It is shown by the dotted line between the SMZ skid and the H skid. We will consider other measures to improve the reliability of the water treatment facilities. We will continue to make efforts to maintain stable operations, reduce the development of radioactive accumulated water, and reduce the risk of the radioactive leakage.